Okay, Unit 7, number 20. Consider the differential equation dy dx equals xy cubed. On the axis provided, sketch a sloped field for the given differential equation at the 9 points indicated. So, first thing is, at 0, 0, we have 0, so we just make a horizontal line there. At 1, 0, we have 0. At negative 1, 0, we have 0. So we have those three horizontal points, and if they are over the line there, make sure just a little bit up, just so they know you drew something there. Okay. At the coordinate point 1, 1 becomes 1 times 1 cubed, or 1. So just drawing a little line with a slope of 1. At 0, 1, we're drawing a horizontal line again because it's 0 times 1. At 0, negative 1, we're drawing a horizontal line again. At the coordinate point 1, negative 1, it says a negative 1 slope. At negative 1, negative 1, it says negative 1 times negative 1 cubed. So a negative times a negative is a positive 1. And lastly, at negative 1x and positive 1y, we have negative 1 as well. Okay, so there's our completed form of part F. Okay, second derivative, in other words, just taking the derivative of the original function right here, xy cubed. Second derivative is going to be a product rule. So I'm going to, for the sake of clarity, I'm going to write this again. All right, and the second derivative is the derivative of the first, which is 1 times normal second plus the derivative of the second, which is 3y squared y prime times normal first. Okay. So the second derivative, which would be the, second derivative of that, all right, is equal to this right here. And then we want to take what we know our y prime to be and substitute that in. So we're going to have d y cubed just remains y cubed, plus I'm going to substitute in xy cubed here. So again, we know our original dy dx is equal to xy cubed. So I'm going to rewrite this whole thing here, and then I'm going to solve for this type of thing, or simplify a little bit. And there you go. And there's your second derivative. Okay, last one here. Find the particular solution, y equals f of x, to the given differential equation with the initial condition f of 2 equals negative 1. Okay, find the particular solution, y equals f of x, to the given differential equation with the initial condition f of 2 equals negative 1. That's the coordinate point 2, comma, negative 1. So here's our original differential equation. We want to move all our y's to one side and all our x's to the other. And then from here, okay, so here we are. We moved the y to the numerator. Okay, here we go. So we're going to integrate both sides. We have y to the negative first, dy x dx. This becomes, I add 1 to get to negative 2, divide by that value. So this whole thing becomes negative 1 over 2y squared. And this becomes 1 half x squared. There's my plus c. Now I want to evaluate it at our given xy coordinate points. So I take my 2, plug it in for x, take my negative 1, plug it in for y, a little bit of basic algebra, and I find out that our c is negative 5 halves. Now I rewrite the entire solved function with, instead of c, negative 5 halves. And my first step to solving this is to combine these two terms. Okay, so once we combine these, what we're going to have to do is we're going to have to flip this, multiply by 2 first, let's say that, multiply both sides by 2, so these go away. This becomes 1. And then flip it and negate it at the same time. When I flip this and negate it, my denominator goes from x squared minus 5, when I flip it, to 5 minus x squared. So that is the thing. So I don't leave the negative 1 to the numerator. I put it on the top. I put it on the bottom. So then from here I have y squared equals this quantity. I take the square root, and I get the square root of 1 minus x, 5x, 1 over 5 minus x squared. And I use the negative solution because my solution is negative. My particular solution is negative. So I have to specify that. So that is my f of x. Okay, last problem. Holy smokes. Okay, here's the differential equation. Looks very involved. dy dx equals this. That's something we'll deal with on a separate note. A portion of the slope field of the differential equation is given below. Remember, every xy coordinate point plugged in here gives a particular slope. Sketch the solution of the curves through 0, 1, and 0, 5 halves. So 0, 1 is right here. So 0, 1 is right there. And the solution, because all those points are horizontal, right there, there's my solution to 0, 1. 0, comma 2.5, or 5 halves, is a little more difficult, but I'm really just following these curves. I just sort of follow the curves and let it sort of go through. And then this is the solution, the particular solution for these 0, 5 halves. Okay? So that's part A. That's it. We just sketch those curves. Okay? Part B. Okay. So now write an equation for the line tangent to the solution curve through the point 0, 5, 2. So as we've said 100 times, equation of the line, we need x, y, and we need slope. Well, in this case, we are given the xy, right? To find the slope, we plug our 0, 5 halves into our original function, right? So 5 halves plugged into y minus 1 is going to be 3 halves. So there's my 3 halves, all right? 0 plugged into 0 plus 1 is going to give me 1. Cosine of my x value is going to be 0, so that goes 0, 0, boom. So cosine of pi, so that's it. So I've evaluated this at 0, comma 5 halves, and this is what I come up with, right? 3 halves, 1 cosine of pi, and the total is negative 3 halves, because cosine of pi is negative 1. That gives us our slope. So we go y minus 5 halves equals my slope, which is negative 3 halves. X minus 0 is excessive, and that's our solution. We could put it into slope-intercept form. We don't have to. Point-slope form is more than acceptable. All right. Last question of progress checks. Part C. Find the particular solution to the differential equation with the initial condition 0, 5 halves. So we're solving for this differential equation. All right, so I'm going to do this on a separate sheet of paper. Okay, so this is our original differential. It looks daunting, but we just follow the exact same rules we've always followed, which is I'm going to get all my y's on one side. So I have 1 over y minus 1 dy, and all my x's on the other. Well, all of these are x's, so I just simply multiply both sides by x squared. Now from here, I integrate both sides. This one is pretty straightforward. ln of y minus 1. Okay, so I want you to take a look at this and pause the video at this point just to see if you have an idea as to how to solve this. This looks really daunting, but let's see if you can figure out a way to solve this. Okay, we're back. So we're going to have to use U substitution. So when we use U substitution here, we want to identify our inside, which is our x squared plus 2x plus pi, and then we do, that's our U substitution, and we take the derivative, and we get 2x plus 2 dx, and we realize, wait a minute, we're pretty close. We wanted x plus 1 dx, we got 2x plus 2, so dividing that whole thing by 2 is going to give us what we want. So now we're feeling pretty good about this. So now we're going to rewrite this side, before I integrate it, I'm going to rewrite this side as 1/2 integration of, now all of this other stuff goes away, and it simply becomes cosine of u du. Now that's a much easier way to deal with this at this point. So here we've already integrated the left-hand side. So now we have to integrate this right-hand side. I'm going to leave this left-hand side exactly the way it is. And I'm going to leave the 1/2 where it is. And the integral of cosine is sine. Right? This is not a definite integral, it's indefinite integral. Remember, when we integrate and get a co, we take this opposite. In this case, we don't take an opposite. So this simply becomes 1/2 sine of u plus c. And we had our u substitution before. So this becomes ln of the absolute value of y minus 1 equals 1/2 sine of this whole big U, x squared plus 2x plus pi. Okay? And then we can use our initial value to solve. Now we're going to solve for 5, 0, 5/2. So we're going to plug in 0 for x, we're going to plug in 5/2 for y, and we get ln of 3/2. We don't need the absolute value anymore. We know it's positive. Equals 1/2 sine of 0, 0 plus pi, so sine of pi. Okay, so ln of 3/2 equals 1/2 times sine of pi. Sine of pi is 0 plus c, therefore c equals ln of 3/2. Now we rewrite the whole thing. Ln of the absolute value of y minus 1 equals 1/2 sine of x squared plus 2x plus pi plus ln of 3/2. Okay? Now when we rewrite this whole thing, we're going to leave the y minus 1 here, and we're going to raise e to this entire side.
Yeah.
And as we've seen over and over and over again, we can rewrite this as e to this times e to this. Remember, because we're doing the reverse rule of exponents. So e to this times e to this is simply going to be 3/2. So this is going to be y minus 1 absolute value equals, remember, this becomes e to the ln of 3/2. Therefore, 3/2 and e this whole thing. Okay? Alright, and then y of 0 is 5/2. Therefore, we know that y is greater than 1. Therefore, we can get rid of the absolute value here. And we simply have y minus 1 equals 3/2 e raised to the 1/2 sine of x squared plus 2x plus pi. And then we finally, to get our final answer, all plus 1. And that's our final answer. Woo! That was a long one. Go through this problem a couple more times if you have trouble with the algebra process. And that, folks, is all 7 unit progress checks, all 21 problems. I will see you Monday.